Hello and welcome to this quick introduction to THERM, which is a software that I have used over the years with my students to calculate thermal bridges and thermal bridge linear coefficients that we want to use in simulation tools. So this is just a very quick introduction of how to get started, and I will do this with a shared screen setting where I walk you through the different steps. Now, I've started off at the Windows and Daylighting website where you can download THERM, and there is a link for the latest versions that I've already downloaded this version. I used a full setup version because I started from scratch, and there are currently right now 2 libraries that you need to install before that. So once you have installed your THERM on your desktop, you should be able to quickly pull it up, and just by typing THERM, and THERM 7.7 is the version that I have, and it opens with a flash screen that I can just quickly click away. If it does, it also goes away after a second anyway. So the first settings when you have it installed, it is that because it's an international software, it's a government agency that produces it, it starts out in SI units, so the standard international units. And you can check that quickly by looking down in the corner here that you actually have millimeters and not inches. And the quickest way to quickly switch to imperial units, or IP units as we call them, is to use this Fahrenheit Celsius switch button that you find all the way to the right. So as a first step, I switch it to the inches, and now you see down there we work with inches. But let's explore a few more of the settings that we very quickly need to change here. You find that by going into the options menu and selecting the preferences, and this is a preference window that has several tabs. So we start in the first preferences tab that comes up by default. Here you should see that you actually have now the inch-pound system, so the IP system, imperial system, versus the SI system. If we use the IP system, we actually need to decide what do we use for the calculation or for the measuring of thickness for our conductivity. And if we use inches, so provide the conductivity per inch thickness, we actually need to switch it to the inch per BTU, BTUs per times inch per hour square feet in Fahrenheit. The outer one, the one above here, would be measuring in feet, so feet per square feet. That's why you only see the feet in the denominator down there. Now, this is all what we need to do in the settings tab. Set it to inches. As drawing options, THERM requires you to set a default canvas, so the area where you want to paint. And it comes from the 50 centimeters, which converts roughly to 20 inches. We usually want to see a little bit more. So I would say you want to define something in the 3 feet area. So let's make it 36 inches in each dimension. That's a good start. That's what we do on the second tab, on the drawing options tab. We do not need to change anything in the simulation tab, and neither do we now if we go to the second row of tabs in the THERM file options. These are mostly programming settings in terms of simulation and how the engine works. But we want to visit the snap settings tab. And here we're having a few options that I would like you to activate. First of all is we want to show the grid, and we also want to snap to the grid. That gives you an immense advantage of quickly drawing. There are different ways of drawing that we will look at later, but snapping to the grid is definitely something that helps us. So if we have very simple geometries, as we look at this in this tutorial, we just go with inches of a grid. Later on, you probably may want to set it to ½ an inch or something that you get a better sense of all the thinner materials that we use. So we're not bound by the grid, but it definitely helps us to draw. And that's actually all what we need to do in the settings window. One thing quickly to how we draw and how we move around in THERM. It's a little bit different to what you maybe used in other software tools. It all happens, the zooming all happens with the right mouse click. And if you click the right mouse click on the area where you want to zoom in, that's exactly what happens. If you want to zoom out, you add the shift key. So you hold the shift key and you right click and it jumps out from where you are. And see, if you do this 3 times, I quickly see my grid appearing in my drawing canvas of what I wanted to use. So these are the inches that I have. Let me go a little bit further in because right now we will not do anything significant. So the next step would be, there's one more zoom setting that we could look at, and that one would be the control and right click. That goes to the drawing extent, but because I don't have anything drawn yet, it actually doesn't make sense and zooms in way too far. So let me go with shift right click out again to something more reasonable that I want to use. So drawing geometries happens with very simple drawing tools. Either you do it by a polygon or you use rectangles if you have something very simple. So obviously rectangles are very quickly to draw. And if I want to just look at an 8-inch concrete wall as a first example, because you always should start with an example that you actually understand and how it performs, where you can do a hand calculation and know exactly what the result should be. So this should be our first goal. Replicate something I can do in a hand calculation that I'm exactly sure that I have a good handle on the software and all the settings and boundary conditions that we are using there. So we're assuming to calculate the U value of an 8-inch concrete wall that we want to replicate here in THERM. Obviously, we wouldn't need that for that matter, but this gives us a good overview. So drawing a rectangle, I use the rectangle tool, and you can use F3 as a shortcut function. I start in my origin. I can later move my origin, but at this point, I just move it around to have a point that I see very well. And I want to make a wall that is 8-inch thick. To see how thick we are drawing, we can check in the lower left corner in the status bar what dimensions we see. So I see now that I just moved 8 inches down. And in terms of width, it really doesn't matter if I draw a foot or 2 feet. For the sake of this experiment here, let's just use 18 inches or something, or maybe 1 or 2 feet. So 24 by 8, that's what I just drew down there. So this is my first material that I defined, which is not really useful in the first place because this material is now defined as a frame cavity. That's how you arrive at THERM when you have it installed and not changed anything yet. The materials we have by default in our library are mostly window materials. And those materials are probably not so applicable for construction applications as we're looking here. So the next step that we really want to do is load construction materials, which can be done in a materials library. For that, we go to libraries and we select the third entry here, the material library. And you see currently, these are the materials that I just pulled down from the other menu up there. And I want to load a different library. So I'll load a new library. Click the load button here. And you find several different libraries in this folder that you may have that has been created for you where the files are located. What you need to pay attention to here is that you have different types of library. You have material libraries, you have boundary condition libraries, and even something called like U-factor libraries. So we want to load now a material library. And if we look at material libraries, you see 2 different material libraries here. One is the NFRC library, which is actually the Windows library that we just have loaded, which I don't want. And there is another one that is more the architectural materials that we want to use now. I also have a backup of a previous version of a library, so you may not see that if you have just started with THERM. So the material architectural library is the one we want to load. I say open, and now I have pulled this library into my selection. By default, it now wants me to give it a different material because it doesn't find the old frame cavity anymore, and so I can just accept that. Now, if I want to calculate a concrete wall, this is not a particle board. It could be that I find my exact material in here. So for example, we have a heavyweight, a lightweight, and the medium weight concrete, and I could just flip to the middle one. Is this exactly the same conductivity that I actually used in my hand calculation? Probably not. So let's check on that. So if we worked, for example, off the ASHRAE handbook material properties, which I can pull up in a PDF form here. So this is the version from 2017 in chapter 26. And you will find how material properties are defined. And then we find examples of conductivities of fundamental materials. It first starts with insulation materials, and I can scroll down further until I find my concretes. So roofing materials, plastering materials, and here it gets now to concrete blocks. And I think finally here, let me maybe zoom in here a little bit better. These are the concretes that I could find. And you really find a wide variety of concretes, mostly depending on the weight of the aggregate that we use. But you see, if we use a medium weight concrete, it would be somewhere in a conductivity between, I would say 1 for lightweight concretes to 5 medium, and 10, 15 for heavy concrete. So this is the conductivity in BTU inches per hour per square feet in Fahrenheit. And so if we go with the medium weight, so in the 100, and would use a conductivity of 5. So let's go back to our materials and check what we have actually here. We use the medium concrete as a material property, and that actually uses a conductivity of 4. So it's on the probably not what we used in our hand calculation. How can we go and change a material now? I can go into my library. So this is the library where we first loaded our entire set. And instead of modifying, because you cannot modify a preset value, but you can create a new one. And you can start to name that. I usually add a tilde in front of it and call it my concrete. And this is something that is helpful to quickly identify what you added to a library. So if I use my concrete, I set the material type as a solid, and I can now put the conductivity to 5 BTU inches per hour per square feet in Fahrenheit. Double check the units that you have the right one. And the emissivity, we'll leave it at the same at 0.9. And if you like, you can put the color that is conclusive, hints at the material that you use. And I just use a gray material here. And that's all I did. So right now it's still the medium weight concrete, but if I scroll all the way up here, I find my concrete up there now, and now it's set to my concrete material that I just defined. So this is the same that I used in my hand calculation with R value of 0.2. Let's double check a few more things. Did we draw correctly? There is the little tape measure that I can use and measure from this spot to this spot, and it says, oh yeah, it's 8 inches thick. So I just want to double check on that. So an 8-inch with a 0.2 resistivity gives a total R value of 1.6 for my entire wall, adding the surface resistances, which brings us to the next problem. Right now, if I would calculate anything, and that is done with the lightning bolt, I would not get any results because I haven't defined any conditions yet. Let me zoom now to the full extent of what we want to have. So control, right click. That's how I get to my total view. Setting boundary condition happens with the BC button. So boundary conditions, if I click that first, it sets everything to a default boundary condition. Once you select the boundary, you will see it's the adiabatic boundary condition. Now, what else do we have in here? Well, again, as with materials before, we have a lot of boundary conditions that deal with spaces, with interior, broken frames, and some shadings. So this is something that is used in the window industry. We have it much simpler in general construction and in general architectural terms. So we want to get the library that is more conclusive for us. Again, we go to libraries. We now select boundary condition library. And instead of using the one we have loaded, we'll load a new library. I do not want to save the current library. Pay attention here. Very often people overwrite an existing library by saving it to a name that they select and they actually think they load. So save a current library. No, in this case, I can always load them back. So these are the boundary condition libraries. The one that was loaded actually is the BC boundary condition library. We want to load the BC-ARCH library. So the one that has architectural values in there. Actually, they are the ones from ASHRAE, and we can compare them later to the document. I will show you that how we double check that the correct surface coefficients are actually used. So currently we use this boundary. We open it and I can close it. So it sets now to a new boundary condition, whatever I had before selected. Let me select that. And right now it's set it to exterior summer. So let's look at these lists. I have an exterior winter and exterior summer. I have various interior ones. So if we keep the upper side as our outside, I probably will put it to exterior winter temperature now. It's indicated to a blue line, and I set the opposite line to an interior vertical surface. You see there are the horizontal surfaces that have a heat flow up or down for ceilings and floors with slightly different surface coefficients. We use the one for walls with the vertical surface, and that's what I apply to the inside. Let's double check these values. So if I double click the boundary, it brings up what's set there. We set it to exterior winter. It sets it by default to a temperature of 0 degrees Fahrenheit. And it has a surface coefficient in BTUs per hour per square feet per Fahrenheit of 6. So if we go back to our ASHRAE Fundamentals handbook, we can find in the same chapter where we found the material properties all the way towards the end, the surface film coefficients or resistances that we actually should be using for our standardized settings. And so if we look up position of the surface, we set the vertical because we use the wall, and heat flow is horizontal. So the coefficient is 1.46. The resistance is 0.68. So we used in the hand calculation the resistances when we add the resistances, but in the software, you actually use the coefficient. And on the exterior side, that's what we looked at actually first, we should find a coefficient of 6. So let's double check. Exterior coefficient of 6. This is the winter condition when we have it cold outside, and that's exactly what's there. The only reason why it's slightly different is because it's rounded back from the SI units, and that's why we have just 5.99. Now, this is perfectly fine. Let's double check the other condition. This is the interior one with the vertical surface. It has 70 degrees Fahrenheit set by default, and 1.46, that is the coefficient we just identified before. Okay, so boundary conditions are set. I can calculate now my simulation. There's a short warning because I haven't set the tag yet, but that doesn't matter. We can still calculate. And here you see by default, it's set to isotherms. Oh, there's actually one nifty change that apparently stuck from my previous installation where I set the results slightly different. I will show you where you can actually do that. And what you see different probably if you just replicated that is that you will not have exactly isotherms at every 5 degrees. So this is a setting that can be found by going to Calculation, Display Options of your results. Now you need to find the Advanced button of these. So by default, it's set to isotherms. With advanced settings, I can set my isotherm settings to have a minimum. Again, I have some comma roundings, decimal roundings there. I started at, let's say, with -10. Maximum is at 80 because I know I just go to 70 and I want to have every 5-degree isotherm. That's how you end up at nice numerical values for isotherms, much easier to read than the comma and decimals that you have to decipher otherwise. To calculate a U value, you need to tell THERM where you actually want to count the heat loss. And you can do that on either surface. And we can double click the interior surface for now, and you see right now we did not add a tag for as a U surface. And the tag that you use here is just a label that can be literally anything you want to call it. And by default, again, because it comes from the Windows side and the Windows simulation, it has edge, frame, and some of those tags you would use over there. This is the third library we could load, but rather than loading a library, I will show you how you manipulate the library now quickly, because it's really just a list of tags. And we, for that, go to the U factor surface library, which is a simple window of all the names that we have right now. And I just want to get rid of those. I don't need a frame. You cannot delete the none, even though you can delete that. I want to just, what happens if I delete the last one? All are gone. So now I don't have. I want to add one that let's call interior side. I want to add another one that's called exterior side. I will create another one that I want to use later that I call corner inside. So these are just names. You can call it anything. If you like, you can even call it Georg. And that's all I needed to do here. So because I tag it to the interior side, that's why I want to calculate how much heat flow is now crossing here on the interior side. Now that we have done that, the results need to be recalculated. And once we hit the lightning bolt, the results look very similar. But now if I go to U, to these U buttons, I see the U factors that have been calculated as part of this simulation. And right now it says nothing available because it by default jumps to the projected Y direction. And in the Y direction, nothing is flowing because actually our surface is along the Y direction. So we need to look actually at the X in projecting towards the X direction, or we just go to the total length. And with the total length, we now have a U factor that is calculated from the simulation and averaged for the length where it's calculated per square foot and per 1 degree Fahrenheit. So it really doesn't matter what your temperatures are on either side. All you need to have is a delta T that is in place at first, and then it calculates of how much per 1 degree of this delta T would actually be transferred. So this gives you the conductance of the material as it's placed with the surface coefficients right now for our example. If you prefer the R value, you can switch to that. So we see an R value of 2.45. So the last step now would be to compare this to a hand calculation where we know what we're doing. And if we assume a very simple material setup where we had a concrete that had conductivity of 5, as we said, then the resistivity and maybe we should write that out. These are BTU per hours per square feet per Fahrenheit. So I write it in BTUH, which actually means BTU per hour. And if I convert this to a resistivity, then it's nothing else than the inverse of the same let's go here. So 0.2. Now we actually would have, if we want to write it out, the square feet Fahrenheit per BTUH. This is the resistivity. We can add up resistivities. What's the thickness that we use? We had 8 inches, so we can multiply the thickness to get our total resistance of the material. And if we do that, then we have 0.2 times 8, the 1.6 as the total resistance of the concrete. Now we need to add the, so actually the total resistance would be over here. It's very similar. It's just not per square feet and Fahrenheit. Oh, that was the mistake. So it is square feet per Fahrenheit here, but I missed out the inches that need to go in here. Here are inches, and then the BTU times inches. Actually, that's a little bit, let me double click on this to make the width a little bit better readable. Everything centered here, maybe even here. So the only thing that is missing in our test is the exterior surface and the interior surface. And if we look up the resistance values again in the ASHRAE table, on the resistance side, we have 0.68 on the inside. And if we use winter as we did before, we would have 0.25 on the 0.17 on the outside. So exterior surface 0.17, interior surface 0.68. And if we build the total of that, it should be 2.45. So this is my R value. And if I want to have my U value, then it's nothing else than the inverse of it. So 1 divided by that, what we have up there. And this would be 0.4081. So going back to my THERM calculation, U value is 0.4081. We have 78. Close enough. This is rounding error that can happen in simulation, but now we have exactly replicated what we actually did. Here's one more piece that I wanted to explain in terms of boundary conditions. So while we loaded the architectural boundary conditions that come with the software, you can obviously define your own boundary conditions. For that, let's just go to the exterior side here. This one that I used from the ASHRAE table set the temperature by 0 degrees. It set the heat coefficient with 6. If I go to the boundary condition library, I can, similar to the material library, create my own now. I create a new library and again use my, or whatever else you want to call it, exterior temperature. Just exterior. I use the tilde just for my own sake, that I find it faster. You could actually leave it, that it always shows up at the end of the listings. What do we set for that? We use a simplified model. There are comprehensive radiation models that we don't want to explore here. I set an outside temperature now. Instead of 0 degree Fahrenheit, I will set it to 10 Fahrenheit, which is much closer to what we do here in Blacksburg. The film coefficient now is set to 0. Careful, if you set that to 0, it is actually a superconductive material. It has a super resistive material. It basically creates a super insulator on your surface. Conductance of 0, because that's what the coefficient actually explains of the air film, would be super wrong. We need to put the 6 if we want to follow ASHRAE recommendations. So that is the the 1/6, the 0.17 we used at the resistance. And you can actually also set the relative humidity, but that is not done per boundary condition. That is actually done for the entire scope. It's usually applied to the indoor air if you want to look at surface conditions, surface condensation risk. So right now, just ignore it. It will not be stored with the exterior. It's just a program setting that we will use later. We set just the temperature and the surface coefficient in a simple model. Oh, one more thing, what we could do is we can set the color for that. And if I want to differentiate from the default blue one, maybe I use the lighter blue one for this one and save it from here. Once I close it, I can now select it. Here's my exterior and my winter, setting it now to 10 degrees Fahrenheit and the same surface coefficient. And once I have that done, I can calculate the model again. And now you see it meets at 10 degrees Fahrenheit on the outside. This is the 15. We have a little bit of resistance on the surface. That's why the surface is actually already slightly warmer than the 10 degree that we have outside. If you are really curious of how warm the surface is, we can use a tool that allows us to view the temperature at a certain point. And so you find that in the view menu, temperature at cursor, that gives you a little measurement window, and wherever you run your mouse now, you can read the temperature. So if I go to the surface here, 14.1 seems to be the surface temperature. So we gain roughly 4 degrees from the outside just with the surface film that we have there to our outside surface. On the inside, it should be actually more. While we start off at 70 in our space, our surface, you will see, arrives somewhere at 53 degrees Fahrenheit. So you have a steep drop because the inner surface resistance is actually bigger and the total resistance of the concrete is not really much. That's why we have pretty steep drops from the inner temperature, inner air temperature to the surface temperature. So in this brief video, I have just shown you how you can quickly double check that you actually know what you're doing in a simulation software. It's fundamental to understand and be completely in control of the properties and the elements of simulation that you use, and always double check it with a solution that you know from a hand calculation. And before you haven't arrived there, I would not trust my own results.